In the past, I did a big study of pattern-welded Damascus, but I always get comments that why haven't I tested the true Damascus, Wootz Damascus, also called Crucible Damascus. Which type of Damascus is better? Which one performs the best in terms of toughness and edge retention? Let's find out. So Wootz Damascus is a very different thing than pattern-welded Damascus. Both are called Damascus. Wootz is the older of the two. They are called Damascus primarily because they both have a pattern, but they get it in very different ways. Pattern-welded Damascus is two or more steels welded together, forged welded together through diffusion bonding. Wootz Damascus is also called Crucible Damascus because it is made with a single material. It's typically made in small ingots called cakes, where they make it with a high carbon content and process it to get microstructure banding within the material, which causes the macroscopic pattern. I worked with bladesmith Spencer Sanderson on this study. He has made Wootz in the past. He's very good at it. What he does is he starts with electrolytic iron flake. That's a high purity iron source. Then he adds pig iron, which is a high carbon, though also somewhat high impurity level type of iron. It's an intermediate product during steel making. So they smelt iron ore with coke, which introduces a very high carbon content to turn it into iron. Then he also adds a little bit of ferroniobium as the carbide former. The ancient material, what Dr. Verhoeven found is that there was a very tiny amount of vanadium in the iron ore that they started with, and that carbide former makes it possible to cycle the steel and get the carbide banding. But Spencer adds a little bit of ferroniobium. So what he does is he adds those ingredients to a crucible, he tops it with green glass to form a protective slag, and then he seals the lid to prevent oxidation. He puts it in a furnace at 2900 degrees Fahrenheit and holds that until it melts, after which he slowly cools the crucible and the steel solidifies. Then he holds it at high temperature called a roast, and then he forges it down. The thermal cycles that the steel goes through during the forging leads to the final carbide banding. If you overheat the steel, all of the carbides dissolve, and then they re-precipitate or reform throughout the steel relatively evenly. But if you don't dissolve the carbides, you heat up to an intermediate temperature during the thermal cycling or forging process, the carbides will coarsen in the areas that are high in the carbide former. In this case, niobium, but it could be vanadium or chromium or manganese even. Those rich areas, the carbides will coarsen, and in the carbide lean regions, the carbide former lean regions, the carbides will shrink during the thermal cycling process. So the more thermal cycles you get, the more banded the microstructure becomes until you get carbide bands that lead to the pattern. So I measured the composition of Spencer's Wootz that he sent me with optical emission spectroscopy and also LICO combustion. OES is a very good technique, though its carbon and sulfur measurement is not as good as LICO because they are very light elements. The combustion method is very good at measuring the light elements. So the carbon turned out really well, 1.59. That's right around the average of ancient blades, which is approximately 1.5% carbon. As we mentioned, that high carbon is necessary to get a wide two-phase region so that overheating during the thermal cycling is not as likely. The more carbon, the higher the temperature it is that those carbides survive before they dissolve. We also added a little bit of manganese for hardenability, 0.18%. And that's because we needed some hardenability. Hardenability is not how hard the steel can get, but it is how slow we can cool the steel and it's still fully hardened. So you can have a high hardenability, low carbon steel that doesn't get very hard, but you can cool it in air and it still gets as hard as it will get. Spencer actually sent me some steel originally that had little or no manganese, and I could not harden it in oil at all. And I actually still had difficulty hardening this steel even with 0.18% manganese, which is not particularly high. We also measured about 0.13% phosphorus and 0.13% silicon. That likely comes from the pig iron. Pig iron can be high in silicates. Those are silicon oxides. And it also has other impurities in it like phosphorus. So that is likely where those impurities come from. Luckily, phosphorus is pretty common in ancient blades when they have measured the composition of them. So overall, apart from the niobium addition, this Wootz looks very similar to ancient Wootz, and I think it'll be a good steel to test and compare to modern steels. So as I mentioned, that first piece of steel he sent me with the very low manganese content, I heat treated it and couldn't get it to harden. So Spencer told me he normally uses 1425 Fahrenheit for 6 minutes and then quenches in Parks 50. I copied that heat treatment, but I got very inconsistent hardness readings, which likely indicates that some perlite was forming during the quench. And then in the second set, we had the higher manganese. I also bumped up the austenitized to 1475 for 10 minutes, which is more typical of what I do with simple high carbon steels. But even then, I was still getting a little bit of perlite in it. You can see in this fracture surface of steel that I quenched in Parks 50, and this was only just barely over 2.5 millimeter, which is the final dimension for my toughness coupons. We could even see in the fracture surface these little black spots, which were the perlite. And when we did the microscopy where we etched it, we saw these black dark regions with what are called lamellae in there, which indicates a perlite structure. Perlite is what happens when you cool the steel too slowly. Like if you cooled it in air, it would basically be all perlite rather than martensite. So we don't want perlite. It is soft and it's even somewhat brittle. So you get a bad microstructure for a knife. We need all martensite. So eventually I learned that I had to quench in water. So through trial and error, we learned it had to be water. It's a very low hardenability steel. And that is for two reasons. One, the low manganese content that we mentioned before, and also the high carbon content. So with high carbon, the driving force, or how much the steel wants to form perlite, is higher. So perlite is a high carbon phase. It's alternating bands of ferrite and carbide. The more carbon you have, the more the steel wants to form carbides as it cools down. So with the very high carbon and the low manganese, the hardenability is low, and we needed a water quench. Now, Spencer using 1425 for 6 minutes, it probably is working for him because he has a forged blade going into the heat treating. So it's thinner near the edge, which is the main part that needs hardened. You can see that in one of his previous blades, he has a hamon. So with a partially forged and or ground blade, you have the thinner edge, and that area is easier to harden, and the spine is thicker and will not harden as easily. And you can even add clay to slow down the cooling further at the spine. And so getting a good hamon typically indicates that you have a low hardenability steel. So when I finally got this steel to harden properly in water, I was getting around 67.5 Rockwell as quenched. That's typical for a high carbon simple steel. And we did a 450 degree temper, which led to around 60 to 61 Rockwell. 450 degrees is a relatively high temperature. We gave it a little bit more temperature to bring down the hardness more because this is such a high carbon steel. We wanted to give it the best chance possible for the toughness test. So we tempered at 450. If we went any hotter, we would probably start to get tempered martensite embrittlement. And when that happens, the hardness goes down and the toughness goes down. So 450 we felt was the right compromise to get the toughness as high as we could for this high carbon Wootz steel, while also maintaining some hardness and avoiding tempered martensite embrittlement. Looking at the microstructure at a little bit of a low magnification, we can see clear carbide bands. This is what gives us the pattern. This is what gives Wootz its unique properties. So we got great banding in this material. So Spencer's doing a great job for mimicking the microstructure of Wootz. You can also see some gray elongated features in the steel, which are the impurities, also called inclusions. This steel has a relatively high content of them. One way to look at the impurities without the rest of the microstructure is to look at the steel as polished rather than etched. And when we looked at it in as polished, you can see these black elongated features and also the black dots in the micrograph. Those are all of the impurities or inclusions. And there were enough of them where we could even see them in the sharpened edge under magnification. So again, we've got these black elongated features, and those are inclusions in the steel. They are very, very tiny, but they do affect our overall properties as they are brittle. The likely source of the impurities was the pig iron, which, as I said, is not an especially clean material. Another issue is that this is made, in Spencer's backyard. Basically, we're using simple steel making methods. These are not big commercial steel making facilities, and so there can be more impurities because of that. Also, Spencer told me that when he normally forges these ingots, he forges all of the junk material that ends up on the top of the ingot to one side and then grinds it away. In this case, he decided to keep it in the center of the billet to grind it off of the surface. And you can see some pictures here. He circled them where the junk of the original ingot is on what becomes the center of the steel, and he was concerned that maybe some of that got forged into the material. That is one possibility. We don't know for sure, but I thought I would point that out. So we measured the toughness of the Wootz with my standard Sharpie impact test and compared it to other low alloy and simple carbon steels. So when controlling for hardness around 61 Rockwell, Wootz had the worst toughness of the low alloy steels. This was basically expected. One reason is the impurity content, the inclusions that we were talking about before. So Pertula looked at the effect of phosphorus content on Wootz in a previous study because there can be relatively high contents of phosphorus in these ancient Wootz materials. And as expected, he found that the higher the phosphorus content, the lower the toughness. So that's one reason why the toughness was relatively low. Another is the very high carbon content. So in general, the higher the carbon content, the lower the toughness. So here is a plot of other low alloy steels versus carbon content, and as the carbon content goes up, the toughness goes down. One reason is that more carbon can be in solution, so the martensite itself is higher in carbon. That can lead to plate martensite and other factors that lead to lower toughness. The other thing is the high carbide content. So more carbon means higher carbide content. Carbides are brittle particles. The more of them you have, the less tough the steel is. The other reason is the banded carbide structure. So bands of carbides are worse for toughness than evenly distributed carbides. So again, Pertula, he did a study where he looked at 1075, that's 0.75% carbon, versus a 1.58% carbon Wootz material, very close to the carbon content we are studying. As expected, the 1075 with lower carbon had significantly higher toughness at the same hardness. But he also did another interesting study where he treated the Wootz to have a uniform carbide structure versus the banded Wootz-like structure. And with the uniform carbide distribution, the toughness was higher because he didn't have carbide bands anymore. So the Wootz had relatively poor toughness because of the high inclusion content, because of the high carbon content, and because of the carbide banding. So Wootz is not the best choice for toughness. I also measured slicing edge retention in the Catra test, which I've talked about lots of times on my website before, knifesteelnerds.com. It's a slicing test. It does 60 or 120 back and forth strokes called 60 cycles, and it cuts 5% silica impregnated paper. So this is a good test because it wears the edge relatively quickly. And when we looked at the result of the Wootz and the Catra test, it approximately matched 52100. 52100 is among the best of the low alloy steels because of its 1.5% chromium content, which increases the hardness of its carbides. So this is a pretty good result for Wootz, given that it's basically just carbon and a tiny bit of niobium. By the way, that tiny bit of niobium is not enough to improve edge retention. That's a very, very low volume of carbide. The niobium is basically just for the carbide banded structure, and it's also added to a lot of steels to help pin the grain so they don't grow very much. The carbide banding also helped. So we've seen this in other steels, like in the study I did on 8CR13 MoV that had some banding in it, and that helped its edge retention. We also saw that in pattern-welded Damascus, where we intentionally got a banded structure, and that also boosted edge retention. So the edge retention of the Wootz was helped by the high carbide volume and also the banding. Dr. Verhoeven also did a Catra test before with Wootz AEBL 52100 and 1086 steels. And there were some interesting things there because in that study at 60 Rockwell comparing with 52100 and 1086, Wootz did the worst. But when tested around 40 Rockwell, the Wootz did the best. Now, I looked at this study and I was a bit mystified by it, but I think what happened in the study was inconsistent sharpening. Because if you look at cut number 1 in the Catra test, the Wootz Damascus was already the worst cutting steel. And so if the edge is not good at the start of the test, then of course it's not going to cut as much overall. But with the 40 Rockwell test, the Wootz started out the highest, and of course it cut the most over the course of the test. So I think what happened was just inconsistent sharpening, because with the 40 Rockwell, the 52100 did the worst. And I can't think of any obvious reason why 52100 would suddenly become the worst steel at 40 Rockwell when it was the best at 60 Rockwell. So I think it was inconsistent sharpening rather than some issue with Wootz. So Dr. Verhoeven had previously proposed that the carbide bands were not crossing the edge in a beneficial way, but I think this inconsistent sharpening is the more likely explanation. Preemptively answer some questions that might come up. The reason why both Pertula and Verhoeven tested Wootz steel at relatively low hardness, like 40 Rockwell, was because a lot of the ancient blades that have been tested had a perlite microstructure. And that was in part because quench and tempering wasn't very common yet anciently, and also because the hardenability of the steel was so low. So even if they were quenching and tempering it, it may not have been achieving a martensitic microstructure. So edge retention and edge strength of ancient Wootz blades would likely have been relatively low because they often had low hardness, compared with modern Wootz steel that we can make, which can be cleaner, and we can control the carbon content better, and we can achieve 56 to 62 Rockwell like other modern knives. Another thing people might ask is whether these modern recreations of Wootz match the properties of the ancient material. I think the answer to that is yes. The microstructures of the ancient materials look very similar to those that are achieved in these modern recreations of Wootz. There's some crazy studies out there claiming there are things like carbon nanotubes and stuff in ancient Wootz. Even if there was, it wouldn't necessarily improve properties. I think it's very unlikely. But I think even though there's a small niobium addition in this material versus a tiny vanadium content in the ancient ore, I think the properties are likely pretty similar. Another thing that has puzzled me the more I think about it is exactly how do we define Wootz? Meaning, if there's a banded carbide structure that results in a pattern, is that Wootz? Or are there other restrictions? So is it only Wootz if it has a composition similar to ancient blades? What if the composition is similar, but it didn't begin with a small crucible or ingot of steel? So sometimes people call Wootz steel crucible Damascus because they believe it needs to be produced in a crucible. What if it had the same composition, but we didn't make it in a crucible? Is it then not Wootz anymore? What if it's a modern steel in a giant crucible or some other method? Is it Wootz? What is Wootz? I don't know. I've never heard a solid definition. So, we can try to copy the ancient material, but we can make steel in very different ways and with very different compositions and still get a banded microstructure through various processing methods. And some people have pushed the definition of this in the past. So Ed Fowler, he began seeing a banded structure in his 52-100 because of the many low-temperature thermal cycles that he would put the steel through. So as he added more and more normalizing cycles and grain refining cycles, and he kept lowering his forging temperature, he eventually started to get a banded structure, and he started to call this 52-100 Wootz. He has a DVD about how to make it. And 52-100 is a pretty good choice for this because the high chromium in 52-100 also increases the size of the austenite-cementite region, just like having a high carbon content does. So can Ed Fowler properly call his material Wootz, even though it's using a modern 52-100 steel? I'm not sure. Some knife makers will also etch their commercial steel knives because they have carbide banding in them just due to the alloy segregation and carbides and everything that the steel company cannot get rid of. When you have a high alloy content, those carbides will dissolve at the melting temperature. They can't get rid of them. And so carbide banding is basically just a natural result of making the steel. And most of these knife makers don't call it Wootz, but this feature is seen as desirable to some knife makers and some buyers. So like, for example, this is a knife by Dan Bidinger. I don't actually know how to pronounce his name. And it's made in A2. He gives it a light etch, and it has a very cool macroscopic banded structure that looks very similar to Wootz. Could you call this Wootz? And so I think this is somewhat funny, but the earliest high carbon stainless steel would also have a banded structure. So I think the original stainless Damascus would be just any high carbon stainless steel that they make. So maybe this is a pointless detour. Maybe no one cares, but I don't know what the definition of Wootz is. It could be anything. We could make all sorts of different compositions and get a Wootz-like structure. Maybe we'll even explore that in the future, try to improve the properties of Wootz using our modern understanding of steel and alloy design. But I still don't know the definition, and I think there could be a lot of other compositions we could explore that could be potentially interesting. Okay, now the big question, what's better, Wootz Damascus or pattern-welded Damascus? Or is Wootz still better than modern steels? There's tons of legends about the performance of Wootz cutting the silk scarf out of the air, or whatever the legends are. What is better, Wootz or pattern-welded Damascus first? So they're very different materials, and they can be a whole range of different things. In my Damascus study, we looked at all kinds of different steel combinations, stainless steels with high carbon steels and different types of stainless steels and high carbon steels, and you can get a whole range of properties. So what pattern-welded Damascus are you comparing? Then, as we mentioned, we can make Wootz Damascus with a whole range of compositions. So which Wootz are we comparing to? So I think the question may not have that much meaning, because we can have a whole range of properties of pattern-welded Damascus. We can have a whole range of properties of Wootz Damascus. I think we can say somewhat confidently that the ancient Wootz material does not match up to the properties of modern material. We can make steel cleaner, and a uniform carbide structure is typically better for toughness. The banding does help in edge retention, which is a plus. But I think if we want more balanced properties, we can make better steel today, especially if we alloy it up. High alloy powder metallurgy steels, we can have better toughness and better edge retention and better corrosion resistance than ancient Wootz. If we compare to a more similar steel, another ultra high carbon simple steel like 26C3 that has 1.25% carbon, its toughness is significantly better. 26C3 has smaller, more evenly distributed carbides. So here is the microstructure of Spencer's Wootz. This is oil quench. There's a little bit of pearlite in there. We're looking within a carbide band. These carbides are bigger than the carbides in 26C3. Those bigger carbides reduce toughness. Of course, its edge retention is better, the Wootz's. But I think overall, we can make better steel today than we could back then. This is not a very controversial thing generally, but occasionally people want to argue that the ancient Wootz is the best stuff ever and that we've never matched it. You know, just like we can't recreate the Egyptian pyramids or something. But we could expand this. You know, we could make a lower carbon Wootz with high chromium similar to 52100, and it would have better properties than the simple carbon Wootz. So maybe in the future we will test some other compositions of Wootz. We'll have to see. We'll see if people are interested, if bladesmiths like Spencer want to make more for study. So I'll let you know if we do that later. So to summarize, Wootz Damascus, it's a high carbon steel with carbide banding in it. That carbide banding creates a macroscopic pattern, especially when etched. So we get the banding through a combination of high carbon content so that we can thermocycle without overheating and dissolving all of the carbide. And usually a little bit of a carbide former is necessary, such as vanadium, niobium, chromium, or manganese. In this case, we studied one with a small content of niobium. The banding of the carbides does help with edge retention, but it's also bad for toughness, so there's a trade-off. The low hardenability of simple Wootz compositions makes it difficult to achieve full hardness without a water quench. I could not get full hardness without a water quench. What counts as Wootz is still not clear to me, so I think bringing up that discussion was important here. Maybe we can come up with a definition, maybe we cannot. Overall, it was fun to test this ancient material, and maybe we can look at some other compositions of Wootz later, like something with lower carbon and higher chromium. We'll see. Anyway, this was a fun one. Thank you to all of my Patreon supporters. So Spencer, he donated the steel. He wouldn't take payment, so thank you, Spencer. Sean Houston, he did the metallography, but there's lots of other costs involved in testing all of these steels. All dollars donated to Patreon go towards steel experiments and more fun studies and videos like these. So if you are interested in supporting more studies, please go to patreon.com/knifesteelnerds. Anyway, thank you for watching. Please like and subscribe. Until next time, bye-bye.